Have you ever looked up at the night sky and wondered what the universe is really made of? We see stars, galaxies, planets. But all of that, everything we can see and touch, makes up less than 5% of the entire universe. So, what's the other 95%? Well, a huge chunk of it, about 68%, is something scientists call dark energy. But what is it? That's one of the biggest mysteries in all of science. To understand dark energy, we need to rewind the clock about 100 years. Back in the early 20th century, Albert Einstein published his theory of general relativity. It was revolutionary, describing gravity not as a force, but as a curvature of spacetime caused by mass and energy. Initially, Einstein's equation suggested something weird. The universe should either be expanding or contracting. It couldn't be static, but at the time, everyone believed the universe was eternal and unchanging. So Einstein added a little something to his equations to balance it all out and keep the universe stable. He called it the cosmological constant. It was like a hypothetical anti-gravity force pushing space apart, perfectly counteracting the pull of gravity that was trying to pull everything together. But then in 1929, an astronomer named Edwin Hubble made a groundbreaking discovery. He observed that distant galaxies were all moving away from us, and the farther away they were, the faster they were moving. This was the first concrete evidence that the universe was, in fact, expanding. Hearing this, Einstein famously called the cosmological constant his biggest blunder. He realized he didn't need it after all. The universe wasn't static. For decades, the cosmological constant was mostly forgotten, a footnote in the history of science. Fast forward to the late 1990s, the big question in cosmology was, what's the ultimate fate of the universe? Most scientists thought the expansion was slowing down due to gravity. The gravity from all the matter in the universe should be acting like a brake, pulling everything back together. The only question was whether it would slow down enough to eventually stop and recollapse in a big crunch, or if it would just keep expanding forever, but at a slower and slower rate. To figure this out, two independent teams of astronomers set out to measure this deceleration. They used a special type of exploding star, called a Type Ia supernova, as a standard candle. These supernovas are incredibly useful because they always explode with roughly the same brightness. So by measuring how faint they appear to us, we can calculate how far away they are. And by measuring the redshift of their light, we can figure out how fast they're moving away from us. The plan was to look at very distant supernovas to see what the expansion rate was like billions of years ago and compare it to the rate today. Everyone expected to see the expansion slowing down, but what they found was completely shocking. The distant supernovas were fainter than they were supposed to be. This meant they were farther away than expected. The only way that could happen is if the expansion of the universe wasn't slowing down at all. In fact, it was speeding up. The universe's expansion is accelerating. This was a mind-blowing result. It was like throwing a ball into the air and watching it shoot upwards faster and faster instead of falling back down. Something was pushing the universe apart, overpowering the pull of gravity on a cosmic scale. This mysterious, repulsive force was given a name, dark energy. And suddenly, Einstein's biggest blunder, the cosmological constant, was back in the spotlight. It was the simplest and most straightforward explanation for this cosmic acceleration, a constant intrinsic energy of empty space itself. So what could this dark energy be? The leading theory is that it's the cosmological constant, the energy of the vacuum. According to quantum mechanics, empty space isn't truly empty. It's fizzing with virtual particles that pop in and out of existence. This activity could give space itself an inherent energy. This vacuum energy would have a strange property. It would create a kind of negative pressure, which acts as a repulsive force, pushing spacetime apart. As the universe expands, more space is created, and with it, more of this vacuum energy. This creates a constant push that drives the accelerated expansion. It's a neat idea, but there's a massive problem, often called the cosmological constant problem. When physicists try to calculate how much vacuum energy there should be based on quantum field theory, the number they get is absurdly huge. It's about 10 to the power of 120 times larger than what we actually observe from the cosmic acceleration. That's a 1 with 120 zeros after it. This is one of the biggest discrepancies between theory and observation in the history of physics. Clearly, we're missing something fundamental about how gravity and quantum mechanics work together. Because of this huge problem, scientists have proposed other ideas for what dark energy might be. One alternative is called quintessence, unlike the cosmological constant, which is, well, constant. Quintessence is a dynamic, evolving energy field that fills all of space. Its density and pressure could change over time. This could mean that the strength of dark energy wasn't always the same. Maybe it was weaker in the early universe and has only recently become dominant enough to cause acceleration. This could potentially help solve some theoretical problems, but it also introduces new complexities. We haven't found any evidence for such a field yet. Another, more radical idea is that maybe dark energy doesn't exist at all. Perhaps our understanding of gravity is wrong on very large cosmic scales. Einstein's theory of general relativity has passed every test we've thrown at it within our solar system and in our galaxy, but maybe it needs to be modified when we look at the universe as a whole. These modified gravity theories propose changes to Einstein's equations that would cause the universe to accelerate its expansion without needing any extra energy. The challenge here is to modify gravity in a way that explains cosmic acceleration while still being consistent with all the successful predictions of general relativity on smaller scales. So far, no modified gravity theory has been universally accepted. So where does this leave us? We know something is causing the universe to fly apart at an ever-increasing rate. We call it dark energy, and it makes up the majority of our universe. But we're still in the dark about what it actually is. Is it the energy of empty space itself, despite our calculations being wildly wrong? Is it a new, undiscovered energy field, or is our theory of gravity incomplete? Answering this question is one of the primary goals of modern cosmology. Huge projects like the Vera C. Rubin Observatory, the Euclid Space Telescope, and the Nancy Grace Roman Space Telescope are being built specifically to map the universe in unprecedented detail. By observing billions of galaxies and countless more supernovas, they will trace the history of cosmic expansion with incredible precision. These observations will help us distinguish between the different theories. Will they find that the strength of dark energy is constant over time, supporting the cosmological constant model? Or will they find that it changes, pointing towards something like quintessence or a modification of gravity? The discovery of dark energy has completely reshaped our understanding of the cosmos and its ultimate fate. If dark energy is a cosmological constant, the expansion will continue to accelerate forever. Galaxies will eventually be pushed so far apart that the night sky in the distant future will be dark and empty, with no other galaxies visible. It's a lonely thought, but it's also a thrilling one because it means we live in a very special time in the universe's history, a time when we can still see other galaxies and uncover these profound cosmic secrets. The story of dark energy is a perfect example of the scientific process in action, a theoretical prediction, a discovery that seemingly refutes it, followed by a new, shocking observation that brings the old idea back in a new light. It's a puzzle that has stumped the greatest minds for decades, and its solution will undoubtedly lead to a new revolution in physics. The universe is far stranger and more mysterious than we ever imagined. And as we continue to peer into the darkness, we get a little closer to understanding our place within it. Thanks for watching, and if you enjoyed this journey into the cosmos, be sure to like and subscribe for more adventures into the unknown.